Welcome to this important concept of Fourier transform. We will discuss discrete time Fourier transform. We will show that it is defined only for stable systems. We will now discuss the Fourier transform of discrete time aperiodic signal. This is what we had called as discrete time Fourier transform earlier when we discussed frequency response. Because the discrete time signal is the default signal here, I might even call it as Fourier transform. We will define the Fourier transform of a signal un as follows, which is the same definition I motivated in the frequency response video. Now let us evaluate the same expression for omega replaced by omega plus 2 pi k. Then I substitute on this side also. When you expand it, exponential j into 2 pi k n gives rise to 1. So I get back this expression here, which is nothing but u of exponential j omega. In other words, we see that this u of exponential j omega is periodic with a period 2 pi. Of course, we have seen this earlier. We have seen that it is unique only in minus pi to pi or 0 to 2 pi. Now, because capital U is periodic in 2 pi, it has a Fourier series. This can be thought of as the Fourier series for U. Alright, what is this small u? I can calculate from this expression. Can I express small u of n as a function of capital U? That is a question we ask next. So to do that, what we will do is we can multiply both sides by exponential j omega m and integrate on both sides. So let us do that. Let us multiply this in the first equation, both sides by exponential plus j omega m and integrate. So we had u as the summation and multiply both sides by exponential j omega m, and we are integrating over one period, namely minus pi to plus pi. Remember, whenever we have this integral sign and summation sign, we explore the possibility of interchanging, and we can do that when the infinite sum converges. We had discussed this a little bit in the past while discussing Fourier series. The same discussion is applicable here also. I bring this exponential j omega m term together with this j omega n term. So I get this. Now when I expand this, I first substitute for n equals m and write down this expression. When m equals n, this whole thing becomes, exponent becomes 0, exponential 0 is 1. When I integrate this, I get 2 pi. So I get 2 pi into u of m. Because I have substituted m equals n, I get u of m here. So this is the value of this whole thing obtained for n equals m. What about other values? We have to evaluate. All other terms to be evaluated. Using the same logic as before, we can show that the second term will go to 0. I would want you to work this out. So we get 2 pi into u of m. So I have the expression for u of m from this equation. If I divide both sides by 2 pi, then I will have 1 by 2 pi into u of exponential j omega into exponential j omega m will give rise to u of m. So let me start with that in the next slide. This was the expression we obtained from the previous slide. Next I substitute omega equals 2 pi f. So d omega becomes 2 pi into df. So df equals d omega by 2 pi. So I get this expression. To summarize, this is the Fourier transform pair expression for capital U. This was motivated when we discussed frequency response, and this is the expression we arrived at in the previous slide. In this slide, we will point out an important requirement for discrete time Fourier transform, namely we can take that transform only on stable systems. Because this is important, let us define it once again. This is the definition of discrete time Fourier transform, which is nothing but gk z power minus k with z being substituted as exponential j omega, or capital G of z with the same substitution, provided there is absolute convergence of whatever you have inside this summation. And this can be simplified because you have exponential of j omega k. So you get this expression. Have we seen this before? Can you recall? If you go through previous videos, you will see that this is nothing but the condition for BI/BO stability. As a result, stability condition is required for the definition of DTFT. Why do we say required? Because we demanded absolute convergence, which is the same as BI/BO stability. So a stability condition is required for the definition of discrete time Fourier transform. This is a stronger condition than what we had for Z transform, because for signals such as this 3 power n 1 of n, Z transform exists. Of course, in this particular case we have to choose Z to be greater than absolute Z to be greater than 3, but this is an unbounded signal and this condition will be violated for this system. So discrete time Fourier transform does not exist for this signal, but Z transform exists. So DTFT is defined for a smaller class of signals than for Z transform. This is an important condition, you have to remember this always. So let us summarize. Here is the Fourier transform of discrete time aperiodic signal. We call this the discrete time Fourier transform pair, where we have Fourier transform and inverse Fourier transform or the time domain signal. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.